Good morning, everyone. Today, we are sharing the results of our cybersecurity and machine learning thesis. For the last 2 semesters, we have focused on making digital security more robust. In the background, as you can see, is a cyber digital threat map indicating cyber attacks and malicious activities happening around the globe as we are speaking right now. That's why we are interested in developing an ensemble-based intrusion detection system in order to detect these types of attacks. We have here Mona, Nada, Mohammed, Kareem, and last but not least, Sharaf. Let's dive right in for a quick motivation. One might say that cyber attacks are happening around the globe, but I am far away from being affected by these major attacks. But you need to think twice, because we have an interesting case study. 3 years ago, in my freshman year, AUC had a critical XSS vulnerability, a vulnerability that can affect many AUC users if used maliciously. After going back and forth via emails with Dr. Sharif Al-Qassas, may Allah bless his soul, the issue has been resolved. Sorry. But what was the issue specifically, one might ask? The firewall of the website was operating on rule-based detection, meaning that it checks for if statements if he found an attack vector or not. And that, by design, cannot defend against all malicious and new attacks. That's why we are interested in developing an anomaly-based detection model that can defend against these new attacks. Nada will continue from here.
So to sum up the problem statement, let me clearly say why we decided to choose this topic. We believe that cybersecurity attacks are a serious threat, meaning that they jeopardize multiple systems. So we have decided to create a network intrusion detection system because lately, due to, as Sharaf just mentioned, people have been using rule-based, and that doesn't identify any rare attacks or new attacks that are found. Moving on with our aim, we aim to study and identify a set of key cybersecurity features, and we would like as well to propose a network intrusion detection system. This system is, we're hoping to compete with the state-of-the-art models that are proposed in the literature. Moving on to the objectives or the things that we have been working on for the past year, we first conducted a very thorough literature survey, meaning that we have looked into each and every single developed model for the NIDS. We then compared between public domain datasets, and we chose the best one. We then studied, documented, and proposed another dataset with a really good feature set selection. We then investigated multiple machine learning and deep learning models, and we have decided to go with an ensemble machine learning model. And this machine learning model was evaluated against all of the state-of-the-art models that were found during our literature survey. We finally aim to publish our research paper by the end of this semester. Moving on to the related work with Mohammad Hesham.
So now let's explore areas where existing body of work leaves area for further investigation and improvement. So let's delve into our literature gap. First of all, we have found that the literature use accuracy, and traditional evaluation metrics like accuracy can be misleading in such scenario where we have a significant class imbalance. This does not provide insights about the model's ability to classify and detect instances across all classes, especially minority classes. Next, there is an inadequate preprocessing and feature engineering. There is the absence of the in-depth feature analysis and preprocessing. Models trained on poorly processed and insufficient features fail to capture the essence of malicious and normal traffic. Finally, we found that there is a lack of proper documentation of the literature workflow, which makes it difficult for fellow researchers to grasp the details and nuances that contribute to the model success. And now let's talk about our choices, and let's start with the data set. The nature of the cyber threats, the evolving and dynamic nature of the cyber threats makes it difficult to create data sets that capture the complexity of real-world scenarios. To ensure the effectiveness of our ML models, we chose a representative data sets that capture a diverse network traffic. We chose the NF-CIC dataset, which has a standard feature set, which is captured using the NetFlow metadata protocol. Having a standard feature set is crucial and essential for developing and evaluating ML-based models, and it also helps bridging the gap between the academic research and the deployment of such systems. But the nature of the network is having an significant imbalance. So most of the traffic is usually normal, with only a minority part as an attack. As you can see here, 88% of the traffic is normal, with only 12% as an attack, with a class like web attacks with a mere 0.02%. So we have an obvious class imbalance. However, our dataset has 43 features and 19 million entries. And now I will leave the floor for Mohammad Sharaf to explore the pre-processing and feature engineering that was done on our dataset.
Okay, also let's go quickly on this feature set. In order to have a good and perfect model, you need to do a lot of feature engineering. And literature already did feature engineering, but they did it as well enough. They mostly utilize principal component analysis and another mathematical features that relies on variance to define the important features, and that's not by design how real-world applications do. In many real-world application, what is good is feature domain-specific knowledge, and features that feature domain-specific knowledge are features that capture important underlying patterns based on domain knowledge. So our contribution is as following. We did an in-depth feature analysis to all features in the dataset, numerical, showing importance to them, and also for the categorical features. We also reshaped some features, did some feature engineering in order to get more info for the model. And our final and most important part, we identified two major problems with the dataset. First, we contacted the authors talking about issue in L7 Proto, which is a feature in our datasets. They have extracted wrong data for this feature. We identified and contacted the authors. And also, we have found another major issue with misclassification of some important features in the dataset. Now, Kareem will continue with the evaluation metrics.
Okay, so after talking about all of this, we need to evaluate some way to evaluate our models that we're going to be talking about today. So we chose to go to precision F1 score and recall as evaluation metrics because we think that those three metrics can evaluate any machine learning model in depth. And we had two choices, either to go with weighted or macro. We didn't go with weighted because weighted neglects the minority classes, which is, as my colleague Mohamed Hesham said, is a crucial part of our thesis project. So one crucial part of our thesis project is to detect the minority classes. So we aim to have a well-rounded model that can detect not only the majority and the majority classes, but also be able to detect the less frequent but can be highly impactful attacks. So that's why we went for macro metrics. Okay, so we need to establish some kind of a baseline to evaluate our proposed models with. So we adopted two approaches. The first approach is to train state-of-the-art models. So we looked at the state-of-the-art models and we adopted their architectures and we trained their models on our data set. And then so this step can be considered as we are trying to find the potential of our developed model. And for the second approach, we looked at the conventional models that are commonly used in the industry, and we also trained them on our data set. So this step can be considered as the industry standard. Okay, so it's important to note that all of our models, the baseline models, have been trained on our refined and preprocessed data set. Why? So that we can draw meaningful conclusions relatively, and we can showcase the contributions that we did to our model. And okay, and also it's important to note that we have picked the highest performing baseline models out of the state of the art and the conventional models. But however, all of the models, baseline models, can be found in depth in our research paper. So here we can find like the average numbers that we can that trained on our data set. So the first two are the baseline models, the conventional models, and the last 4 or 5 are the state-of-the-art models. So we can draw like an average of what the industry standard is. We're gonna be picking the random forest from the baseline models to compare our proposed models with, and we're gonna be picking the ensemble LCCDE, which is a shortcut for the research paper we adopted this model from to compare our to compare our proposed models with. And now Mohammad Elkholy is gonna be talking about the deep learning model and why we didn't go with deep learning and went for machine learning models.
So now that we've established a set of features, did some feature pre-processing and established some baselines with which we can compare our model with, we needed to start experimenting with different models. So first thing that comes to mind whenever someone mentions machine learning is like deep learning, because deep learning has been the go-to recently because it outperforms pretty much everything in almost every task. However, when we started experimenting on this task or classification or detection of minority classes in network intrusion, we actually found that deep learning doesn't actually perform that well. Oh, sorry. So as you can see here, the numbers leave a lot to be desired. However, the numbers can only tell us so much about why the problems are underperforming, or why the models are underperforming. So we kind of wanted to do a deep dive into it and try to figure out what is going on under the hood. So typically, deep learning models, they try to learn features or extract features from whatever input that they have, and then make a classification or prediction. So for example, here, this digit number 4, it has a vertical line, a horizontal line, and then a diagonal line. So the deep learning model would then kind of piece these features together or learn them and give us the prediction, which is 4. And it can do that for all the other digits, and then it maps them to a feature space that is separable. So as you can see here, we have number 4 all the way to the bottom left, and then we have number 6 all the way to my bottom right. So we kind of want to explore that on our own data set, our own features. So as you can see here, it fails horribly to separate the different classes in our own data set. So why is that? It's probably because it's not able to detect which features are able to detect which classes. So we kind of wanted to maybe encode the feature separability into the input first before we feed it into the model. So we did that using linear discriminant analysis, as you can see here. So linear discriminant analysis basically changes the feature into maximally separable features, and then we feed that into our model. But after we evaluated the feature space, we can actually see that the classes are all still clustered together. And that means that our model is not really learning much. So instead of doing that, we actually wanted to force the model to separate the different classes in the feature space. So we kind of did that by taking a matrix of maximally separable vectors and multiplying that by the output. So as you can see here, the classes are much more spread out. However, they're still all clustered together in one group, which is kind of a huge problem because we still cannot figure out which attacks are which. So we had to shift gears. And we chose to shift gears to ensemble learning. Why ensemble learning? Well, there's evidence from literature that it outperforms deep learning model in this task. Additionally, it can help with minority class detection because it can build on weak learners to make one strong learner. So if a weak learner is able to detect one class, and another weak learner is able to detect another class very well, we can kind of combine them together to have a strong learner. And next I'll leave the floor to Mohammed Hesham to talk about our proposed experiment.
So let's talk about our proposed models. And let's start by the first experiment is developing individual binary classifiers. But why? Individual binary classifiers focus on a specific class, mitigating the challenges posed by class imbalance. Also, individual classifiers are tailored to recognize patterns associated with a specific class. This increases sensitivity. So this is the first experiment that we have done with the binary classifiers. We used SMOT to handle the class imbalance. It seems promising, but after investigation, we found that using SMOT with the significant class imbalance that we have caused the model to be overfitting to non-authentic data. So we have gone with the balanced random forest classifier. This classifier is in nature capture the weights and distributions of the classes and give higher weight for the minority classes to detect it more efficiently. So this takes us to our first proposed model, the stacked BRF. So here we have, as the base learners, we have the balanced random forest classifier that we mentioned before. And this is fed to the meta learner to refine and make a more informed classification. So this is the results of this model. So it is not as good as we expected. So this takes us to the next experiment with NADA.
So moving on into our next stacked model that we have proposed, it's a stacked boost model where we, as just Riad just mentioned, where we have the base learners and the meta learners. We fed multiple boost models into the base learners. We fed the ADA boost and the XG boost into the base learners, and then we took the predictions and inputted into the meta learners, and it got way better results than our first proposed model. As you can see here, we got overall better results with almost 10% higher in the precision and the recall. We got even higher results. However, we weren't satisfied, as the minority attacks, we were still getting really low precision and recall results in. So another proposed model is the voting model. Let me first explain what is a voting model. The voting model isn't a yes or no model, as you may think it is. It's more of like, it takes in all of the models, just like the random forest, the light GBM, the XGBoost, and decision tree. And the output of these models are fed into the meta learner, but the output is just it's only based on the weighted average. It takes basically the highest accuracy and feed it into that voting classifier. The output of the voting ensemble model gave us even higher results than we have expected it. It gave us better recall, which we were looking for. And moving on to the sequential model with Mohammed.
So now we want to test basically the sequential ensemble model. And the reason behind that is that we wanted to test the model using different architectures. So we wanted to see what happened when the models are dealt with simultaneously or sequentially. So here, as we can see, basically the models are, the models basically are going to be organized or arranged in the based on the distribution of the attacks. So for instance, we have here the benign. We have here the benign as the most dominant attack, which will be the first model that I use. That data will be fed into this binary classifier, and then we will have two sets of data. Either data points will be classified as of this specific data type. In that form, it will just stop there. However, if the data points were not classified as benign, it will move to the next dominant binary classifier, which is in our case, the DOS attacks Hulk. And we continue with that until we are done with our 15 binary classifiers. However, as we can expect, it was not really, the results were not really promising. It only achieved 49% or 50% recall. And after consulting with our supervisors, we identified the error here, which is basically propagation of errors. So propagation of errors is basically when the model will perform a specific error rate, and then this error this misclassified data, whether false positive or false negative, it will be propagated to the next model, accumulating the error, causing this deterioration of performance. Therefore, we decided to go with the simultaneous architecture. And for this architecture, we tested using 3 models. Our first model is a GRU model. And one may ask here, why did we return back to the GRU model, although we previously mentioned that deep learning was not the most effective? We actually wanted to experiment whether adding more features to the data set would cause a change in the behavior of the GRU model. So what is the data set that we are feeding in the GRU? We have our original processed or refined data set, and then we actually utilized our binary classifiers. We fed the data all at once to these binary classifiers, and the output was then concatenated or combined with the original data set and fed back to the GRU model. So the GRU model, to be more specific, consists of 3 layers of GRU model, and then followed by a dropout layer and a softmax layer just for multi-classification. As expected, the results actually increased. It increased to 70% regarding the recall when comparing it with the sequential ensemble. However, we can still notice that actually machine learning models are way better than the GRU. Therefore, we concluded that we were on the right track to utilize machine learning algorithms instead of deep learning algorithms. So we tested the same architecture, but using the XGBoost model and the random forest model, since these are the most commonly used ML models in the literature. And as you can see here, both of them approximately achieved a recall of 78% recall. However, we can see that the XGBoost model had a significantly higher precision of 94.72% when compared with the random forest. It also achieved higher F1 score. Therefore, this was our preferred ensemble model in the literature, which will in our research paper, which we'll talk about later. And now I will leave the floor to Kareem to talk us through our evaluation and comparing our proposed models.
Okay, so after talking about all of those numbers, we need to compare our results with. Okay, so first of all, we have picked the 2 models from our baselines model we discussed earlier. And then we have the deep learning model, just for reference, to further improve that, proves that we didn't go with deep learning for a reason. And then we have 2 of the best performing proposed models that we have. It's clear that our nth XGBoost model is outperforming all of the previous models. So it's our proposed, the chosen models that we have picked. And now we're going to be talking about the conclusion.
So for our empowerment outcome, we aim to publish a research paper. We did thorough literature survey where we found many gaps in the literature. And in our paper, we actually kind of tackled each and every gap that we found. We first pre-processed and done very thorough feature engineering, and we documented each and every step, which was our issue actually in the published research papers. We then proposed and implemented a state-of-the-art ensemble model that competes with all of the available models right now. How did we know that? By doing comparative analysis with all of the available models. Now.
So to wrap up everything, basically what we've been doing throughout this year is that we utilize the NFCSE dataset, and we use that after extensive literature review, and we've gone through pre-processing steps, and then we implemented our own ensemble-based NIDS, which was consisted of the XGBoost along with the binary classifier as we discussed earlier. And we spent a lot of time extensively documenting each step in our research paper, which we will be publishing in one of these journals. So for example, the expert system with application journal or the sensors journal and so on and so forth. By this, everyone, we reached the end of our journey. We're finally done with our thesis, and thank you for listening.